Thank you so much. Thanks for the introduction, and it's great to be here. Hope you all are having a good day. It's so nice to talk to you. So yeah, I'm going to talk about on reflection. Give a talk on reflection. It'll be clear why it's called that in a second. Let's see. So let me just say up front, this is not a talk about neural rendering or like even about deep learning, although it does play a supporting role. So this is maybe just a, I don't know, think of this as a palate cleanser or something if you're saturated on all these topics like, I don't know, transformers, etc. It does touch on psychology, which I'm not an expert on, and maybe many people here are more expert on than I am. So please, if you have comments or corrections, feel free to say that. And in addition to that, we'll use Slido. So there'll be some audience participation. And if you want to get ready for that, you can go to slido.com and enter code MIT. For some reason, that code was not taken, so I use that. I think you can also ask questions, but yeah, I'm not sure how we want to do questions. Maybe I won't look at, probably you should use Zoom for the questions if you want to add questions over chat. And someone can stop me if they see questions that I'm not seeing. Okay, so with that, so let's get started. So yeah, so imagine you're Alice from Alice in Wonderland and through the looking glass, and you come across a mirror, a looking glass that you can pass through to enter the mirror realm, right? So what would that mirror realm be like? So in the words of Lewis Carroll, the way he describes it, there's a room you can see through the glass, like if you're looking in a mirror. That's just the same as our drawing room, but the things go the other way, right? So it's like the mirror realm is like, it's a universe a lot like our own, but different in subtle ways. Well, some ways that are subtle and some that are not so subtle. Or imagine another thought experiment. Imagine you wake up one day and you're not sure if you're in the real world or a real world that's a reflection of our world. How could you tell the difference? What would you notice? So this kind of theme of mirror worlds or reflected worlds is one that you find recurring in literature, especially science fiction. I don't know, I'm very fascinated with this, just thinking about this concept of mirror world. So one story I really like in this vein is a short story called Technical Error written by Arthur C. Clarke, whose synopsis is written here. So the first power plant to exploit superconductivity has been built, and worker Richard Nelson is laterally inverted, following an accidental short circuit in the facility. Nelson finds himself wearing his wedding ring on the wrong hand. Written texts appear inverted, and coins in his technical diary have been affected. Nelson begins to starve. Normal food does not nourish him because most biological molecules are chiral. Chiral meaning they have a handedness. So if you took one of them and mirror image them, they would not be the same thing and would not have the same effect on you. Okay. And again, I find this kind of thought experiment very intriguing. So let's try it ourselves. Okay, so here's the first audience participation question. Here's an image, and this is either a photograph, a real photograph, or it's a photograph that's been left-right mirrored. So I want you to take a look at it and try and figure out which it is. And so this is a good time to go onto Slido. And I'll give you 20 seconds when I hit the spacebar to enter your guess. Okay, so okay, 38% say yes. Okay, I just have to. I can't see this. Okay, now I can see it. Okay, 63% say no. So you're right, actually. Okay, so well, the majority are correct here. So did anybody not guess? And if you didn't guess, maybe you could say, or in chat say what made you think it was one way or the other. Okay, maybe everyone guessed, but Okay, here's the, I actually modified this image a little bit. Okay, someone in the chat is saying he's holding the paper in his left hand. Okay. Let me bring up a. Oh, I don't think you can see this tool. Okay, so I had a tool that zooms into the screen, but I think I'm not sharing my full screen. Okay. So actually, in the original image, there's some text. You can probably just barely see it. So text is the clearest tell, but I hid that. It's actually kind of hard to see, but if you saw that, you could probably tell. He's holding his newspaper in his left hand. That's interesting. So maybe a right-handed person would be inclined to hold in their left hand. I'm actually not sure. I haven't done this experiment myself of spontaneously seeing which hand I'm holding newspaper in. Another cue, though, is the pocket and the buttons, right? So men's suit jackets have the buttons on one side. I think it's, what is it? It's the left side. Sorry, no, the right side. Well, my right. My buttons are on my right. And the pocket tends to be on the, what is it? I guess looking at him, it's the right side of the jacket. So those are cues that if you knew some cultural norms, you might use. But in general, just looking at it, you can tell that, if there are cues, they can often be quite subtle. And so the mirror universe differs from the real one in ways that are both clear, like text, and subtle, like what way the buttons go. And this is different. This is like intriguingly different from like other kinds of geometric operations, like vertical flipping, where if you vertically flip an image, now suddenly gravity is the wrong way, and the person would fall down. If you left-right flip an image, it's somehow a very similar universe to our own, where like the physical laws are similar, but it's ever so slightly askew compared to our own visual universe. Okay. So, okay, why care about any of this? Well, from computer vision's perspective, I think it's interesting to interrogate the kind of symmetry assumptions we often make in computer vision. So there's a whole, these symmetry assumptions are also both sometimes, subtle and sometimes obvious, but we often assume that in a lot of contexts, we assume that flipping the image preserves it being a natural image. Okay, so I'll show you some of my favorite examples of symmetry assumptions in computer vision that we might want to revisit. So actually, one of the first that I saw when I was like a grad student was this example from a paper called View Morphing by Steve Seitz and Chuck Dyer, where they had a way of like morphing between two viewpoints of a scene, or two viewpoints of two different scenes in a geometrically correct way, like respecting epipolar geometry. And one example they showed it on is the Mona Lisa, where if you left-right reflect the Mona Lisa, the idea is now you essentially have, because people are mostly symmetric oftentimes, you have another view of the Mona Lisa, and you can interpolate between those two views. So here's a video they showed in their paper of interpolating between this different views of the Mona Lisa, and you can create like a fully frontal version of the Mona Lisa, and it relies on the assumption that if you have an image of a symmetric object, you really have two images for free, because you can flip it, and now you have a second viewpoint. And I thought this was just wonderful. This really captured my imagination when I saw this for the first time. I thought this was just great. Another example, which is maybe more subtle, is I can't remember exactly where I saw someone show this, but there's this kind of iconic Time magazine portrait of John McCain from when he was running for president, which since it's frontal, you don't really get a different viewpoint if you flip it, but you do get another lighting condition. So flipping it, now the lighting is coming from the left instead of the right. So I don't know, like you can think, okay, now you're 2/3 of the way to photometric stereo, because you need 3 images for photometric stereo, but you have 2, even though you had 1 to start with, right? And I don't know, I love this kind of thing. And I love a paper, this recent paper, Best Paper Award winner from last year's CPR, where they took this idea of gathering this kind of supervision that you get for free from single views of probably symmetric, I guess in their terms, objects, where if you flip it, now you have a second view, and you can estimate things like depth and lighting, render that view, and that's a training signal for learning those kinds of inverse rendering components. So here's their a nice animation from their paper. And again, I find this kind of thing just super cool and interesting, and I love it. We actually had a version of this with Shangzhe, who's the author of that paper. We have a paper coming up in CVPR this year where we rely on an even more extreme form of symmetry. That's reconstructing surfaces that are solids of revolution or surfaces of revolution from a single view. So what kinds of surfaces are solids of revolution? Well, vases are, because I think like vases are often, pottery in general is made on like potter's wheels that spin as the person is crafting them. So they naturally have this solid of revolution type geometry. And so we use this as a another form of supervision to gain extra supervision for reconstructing both shape and illumination and material properties like specularities from single images. So here's like a nice, these images are from the Metropolitan Museum in New York City collection, where we take, again, single images and learn to predict full 3D models with materials from these. Okay, again, very much relying on the symmetry, the underlying symmetry of these objects, or assumed symmetry of these objects. And finally, the most maybe common one, the most common symmetry assumption in computer vision is this idea of data augmentation with left-right flipping, which is, as far as I'm concerned, pervasive. So in fact, you go back to like even before deep learning, the like deformable parts models from Ross Gershik and others, if you look at their GitHub repositories, you can find, yes, they created virtual examples by randomly flipping images from mirror flipping them left to right. Okay, so and the idea being that if you want to instantly get twice as much training data for your image classification algorithm, well, you can just mirror flip all of your data set and boom, like now you can just gather half the samples you were going to capture. Okay, and this is really where I start to question whether this is a good idea. Like, are we really getting these images for free, or is there some cost? Are these really natural images? Is the assumption that flipping an image gives you an image that's in the same natural universe, the same visual universe as the non-flipped image? Is that really a good assumption? Okay, so and in some sense, like, all the symmetry business is great and it's very helpful for computer vision, but I don't know, somehow it's the ways in which the world that are not symmetric that makes things especially interesting. So I've done a lot of 3D reconstructions of cathedrals in my life, and somehow the one that's I come back to as my favorite is not the Notre Dames of the world, but this beautiful Chartres Cathedral, where the North Tower and the South Tower are different because they were constructed during different architectural eras. Like one was constructed during the Romanesque period, one was constructed during the Gothic, and so it has this beautiful asymmetry. Magritte was, very good at playing with these kinds of ideas. So here's an image that, at first glance, if you just look at it, appears to have some symmetric object, but it's actually asymmetric. In addition to you wondering whether the scene behind this painting looks like this or not. And even things like beauty marks have been used, artificial beauty marks have been used for centuries. In the 18th century, it was a French and Spanish idea of like placing a beauty mark on your face. I don't know exactly the rationale, but I like to think maybe it was to create a beautiful kind of asymmetry. And of course, you have your like modern versions, your Marilyn Monroes of the world, etc. Okay, so let's return to this question of what is the cost of flipping images? Is the visual universe really flip invariant? So here's an image that I took. If I flip it, clearly it's not somehow in the same visual universe. It's like now text reads backwards. Okay, again, text is kind of the first thing that you notice that breaks. But actually, if I uncrop this image, you see that actually the true image is the one on the right because this is an image captured in a mirror. So of course, there are some exceptions that, I don't know, prove the rule. You know, sometimes you have a flipped image that's flipped by natural, you know, optical means like mirrors. And that somehow makes this question even more interesting to me. You know, clearly the visual universe isn't flip and bearing in some fundamental way, even though you can capture flipped images, for instance, by looking at mirrors. Okay. So over time, I've been collecting examples of subtle asymmetries in the world. And so I'll show you some of my favorites, some of the things that are less subtle than text that go wrong or that are not quite symmetric. And if you have if other things of this nature come to mind, I'd love to hear them because I really like these examples. Okay, so some of my favorites are actually, there's this great episode of Radiolab, you know, WNYC podcast called, the segment is called Mirror Mirror, where they show this example. So actually, before I go on, I'll just, so okay, here's another question for you. This is a portrait of Abe Lincoln. Actually, one of these is the real portrait and one is mirror Abe Lincoln. So one is real Lincoln, one is mirror Lincoln. Which of these is real Lincoln? Okay, I'll give you a moment to think about that, and then okay, we'll go proceed to Slido. So this was an example they gave in that Radiolab episode, and I'll explain more in a moment. But first, can you tell which is which? Who is the real Lincoln? Okay, so most people selected B, about 4/5 of people said B, and you're right. Okay, so B is the real Lincoln. Okay, so this is an intriguing difference. This shows that there's some perceptual difference between these two images. And I think, so this episode of Radiolab, you know, had several theories, one of which was like about hair part, like somehow parting your hair one direction gives you a different perceptual effect than parting your hair the other direction. I don't really buy that, but people who are psychologists may tell me whether there's anything to that idea. I suspect what's going, so I think people who are familiar with this portrait choose B. I actually asked my class this question, the computer vision class I teach, and it was much more 50-50. And you know, I suspect that, you know, many people in my class are, you know, I don't know, they didn't take US history when they were in high school, so they may not, you know, recognize Lincoln on sight, or at least this particular portrait. But okay, before I go on, there's one more question. Do you notice a qualitative difference between these two images? Okay, so does one of these two make you feel different than the other of these two? Like, do you get a different, I don't know, set of adjectives in your mind from one than the other? And this is not a quiz, there's no correct answer, so I'll just leave this up for a few moments. Okay, so about 2/3 say yes, and 1/3 says no. And I'm with the yeses. So if I look at B, I see someone who looks distinguished. If I look at A, I see someone who looks, I don't know, I get a very uncanny feeling when I look at A. Now, you could say, okay, so two possible explanations are, there's something about well, okay, let's just first observe that Lincoln's face is fairly asymmetric. So he had a condition called strabismus, which made one of his eyes not kind of move with the other one. So his I guess his left eye kind of floated around freely, you know, somewhat freely. You know, he has this bump, his nose is kind of crooked, his lips are somewhat asymmetric. And so his face is asymmetric, but somehow when I look at this face, it looks more uncanny or more asymmetric, or something just doesn't seem right about it. Now you could say, okay, there's something about the asymmetry that causes a different kind of perception in general. But I actually think it's probably that I'm so used to seeing this portrait of Lincoln, this famous portrait, that I'm used to it being asymmetric in this particular way. And when I see this one, somehow maybe I'm mentally correcting B to be symmetric, and it's enhancing that whatever is happening there is enhancing the asymmetry of A. Again, if you are knowledgeable of psychology, you might have a better explanation of this. But this was this kind of the same example was used in this episode of Radiolab, and was striking. It was striking to me. It was striking to the audience of that show, and it was striking to me when I saw this effect. And by the way, this also is something I've experienced in real life. Like, I grew up in an era where cell phones weren't common, and so actually I didn't see a photograph of myself very often. I much more frequently saw an image in a mirror of my own face, and somehow the person I saw in photographs looked strange to me. Like, it didn't look like me. It looked somehow different than me. To where I didn't like seeing myself in photographs. I much prefer to see myself in a mirror. And I think it was the same thing. Like, it's not that my hair was parted the wrong way, and so I'm seeing the correct part of the mirror, and other people are seeing the wrong part. I think it's probably that I was used to seeing my own face one way, and the version of it in a photograph, which is flipped from how I see it in the mirror, just was okay. There is a Zoom a chat to this effect. Yeah, you do hear about people having a strong reaction to seeing their face unflipped. Like, if you turn off mirroring in Zoom and see your real face, sometimes I have heard people want to turn that off immediately. There's something a little bit unsettling about seeing that unmirrored version of yourself. But again, there might be different explanations for why. Oh, so but this portrait also, by the way, is the teaser of this recent time travel photography paper from UW, Swan Low and other authors, where they generate the picture that would have been taken with a modern camera. Somehow this modern version of Lincoln that they synthesize, I get the effect less strongly. Like, somehow this, I still think B looks somehow more natural, but the effect isn't quite as strong. Maybe they've removed, maybe whatever they do also makes the asymmetries less apparent. Okay, so I just really like asking these questions. So a few more quiz questions. Here's another famous politician. And one of these is mirrored and one of them is real. So yeah, which is the real Obama? You have 20 seconds. Okay, let's see how people did. Oh, sorry, no one actually, wait. Okay, I guess people forgot to enter in. For some reason, it's recording 0 votes. Some people said A over Zoom. Okay, so A is correct. And again, I think this is probably an example where you are, since this is a famous, since this is a well-known portrait, you may just have memorized the way that Obama's face looks in this portrait. Antonio has a comment. When looking at a face, some of us pay more attention to the right side of the face. So when you flip the image, it changes how you weight different aspects of the face. That could very well be true. Yeah. I wonder if that comes from this.
You can check that with you can check it out with eye movements. You can see that there are more eye movements on a particular region of the face. It's not symmetrical.
Interesting. So do you think that explains some of this ability to distinguish flip photos from non-flip photos?
No, but it might explain why you perceive faces as being slightly different when you flip it.
Interesting. Yeah, I see. That could be. That may suggest, for instance, that you can, if you know the portrait, you may memorize the asymmetries in a way, or you may be aware in some level of the asymmetries.
or it's like in this phase, if you were only to show half of the face, okay, so you only show the right half, whether you flip it or not. In both cases, you only show the right half. So now the faces look different now, because you see different.
That's interesting. Okay, maybe I'll try that in some future version of this talk. Okay, so here's one more. Okay, I do want people to enter on Slido if they can, because I'm very curious about what people say in this example. So this is a not well-known portrait. It's safe to say that. This is a person on Wikipedia, and okay, again, one of these is the correct picture, non-mirrored picture, and one is a flipped version. Okay, so look at that for a moment and see if you have any thought about which one might be the true face. Okay, now you can enter on Slido. Okay, which of these is the real person, A or B? So hopefully you can't rely on your memory of this portrait to tell. Some people say A on, okay, one person said A on Zoom. Okay, so, okay, most people said B. Interesting, so most people were right. Actually, this is intriguing. So I gave this talk once before where I flipped the order of the two images. So I had A first and then B. Sorry, in this I had the, I switched the order. I switched one, which was A and B. And most people still said B was the real person. So I think there's nothing to be, well, I'd have to do a bigger experiment here, but for some people, for some reason, for this case, whatever one you show second, people have tended to say that's the answer. So in that previous case, people got it wrong by about the same margin. This is again a small sample size, so I shouldn't go much into this, but I suspect that there's, I guess it's going to show a leaderboard. Congratulations to the winners. I suspect that this is not, it's also very important that I'm not showing them like consecutively, but side to side. I think there's a lot of, my guess is that it's very hard to tell as a person whether one face is flipped or not, unless you're very familiar with that portrait. But again, congrats for the people who got it right. I think it might just be some bias due to how I'm presenting the images, though. Okay. So that's one. Okay, so one example is this. There's something happening with faces to where if you flip certain faces, people can tell. Okay, here's another example of a subtle asymmetry in the world. And actually, this one comes from Antonio and his work with Alyosha on dataset bias. And they point out in that paper that if you do a Google image search for mugs, predominantly you'll see the mug on the right-hand side, and that makes sense, I think, as a right-handed person. The majority of people are right-handed. That's how you would naturally, I think, place a mug in front of you if you're drinking from it. And actually, I don't know if the logo on the mug is supposed to be seen by the drinker or the person the drinker is sitting across from, or maybe put logo on both sides. But maybe also the logo is placed in general so that a right-handed person will see it when they're drinking their coffee or whatever. And this, older research in canonical views, if you ask someone to draw a mug, I don't think this is in their paper, this original Palmer canonical view paper, but I think primarily people would draw the handle on the right. And I think that's only because they're right-handed, and that could just be because it's easier to draw the handle on the right if you're right-handed. If you draw the body of the mug first, it might just be easier to draw it on the right. But again, there's been studies of these kind of canonical views. So this goes back to the question I asked at the beginning. Okay, so if you missed the beginning, the first 5 minutes I asked you to draw a hammer. So I want you to look at your drawing and tell me which of these hammers, if any, okay, I'll have a Slido quiz. You can enter your results in a second. So which of these hammers, if any, your drawing resembles? Okay, so go on to Slido, and you can also enter, like, my drawing doesn't look like any of these, but I'm curious. Okay, interesting. So about equal, okay, slight preference for E actually. E, oh no, okay, they're shifting. Okay, so B, E, and A. B and E are about 25%, but A is not far behind. And the others are represented somewhat too. So B and E. Okay, so about the same number of people drew this hammer as drew this hammer, if I'm reading that right. The kind of vertically oriented hammer and but facing either direction. Okay, so this might be a case where the preference is not totally clear. So I think maybe as a right-handed person, you might hold a hammer so it looks like B, and as a left-handed person, you might hold a hammer so it looks like E. But this might be so. In the past, I asked people to draw a mug, and it just replicated the results that from the sort of canonical view kind of idea. But in this case, it seems much more mixed whether people choose B or E. If you do a Google image search for a hammer, actually, I think you kind of maybe A and B are actually a horizontally ordered. I think if you do a Google image search for hammer, it kind of shows what a right-handed person might see if they put a hammer down in front of them. But it's interesting that people draw it not necessarily in that way. Okay, I'm very obsessed with like searching for Google image searches since reading that note in Antonio's paper. So clothes hanger is another interesting example of maybe a subtle example of preference for one direction. Again, these you can see these are like for sale. So maybe these are just an artifact of how people who want to sell clothes hangers render them. But again, you also have a strong preference for a left-facing hanger piece, which if I were as a right-handed person hanging up a hanger, that's how I would see it. Interesting. Okay, so here's another example of a kind of asymmetry in the world, a subtle one, which is another one I really love. Antonio again is a big average image fan. Jason Salavan, who created these average images, artistic pieces. Also, you observe a striking asymmetries in these 100 special moments of each. So maybe the most striking is wedding portraits. So again, this is somewhat corroborated by doing things like Google image or Flickr searches, but there seems to be an unwritten convention of where the groom and where the bride should stand in a wedding portrait, and maybe a weaker convention about what side a child should be on in the classic, like, I don't know, Santa portrait photo. And I'm not, I think Jason Salavan, when he created these, picked and choose. Like he didn't just take the first 100 images from Google image search. And Alyosha and Junyan have a paper on this as well, but this average explorer. But I think there is something to this until I saw these averages, I didn't realize that there might be these unwritten visual conventions in the world. Okay, I think this may be the last one. There's also a great paper from Jennifer Sun and Pietro Corona called "Where is the Sun?" that explores bias in perception of lighting in imagery and also in artwork throughout history. So there's a well-known preference for interpreting the light source as coming from above if you have an image where the light source direction is ambiguous. So here's an image where either the objects some of them are concave and some are convex and the light's coming from above, or you flip which are convex and concave and the light's coming from the bottom. And most people would interpret this as the light coming from above. But in addition to that, the preference for lighting they showed in experiments is not directly overhead, but shifted to the left. So you can do other experiments that try and gauge whether you have a right or left preference for interpreting lighting. And so there's a slight preference to the left. And this is reflected in artwork in that, like, if you explore artwork until about 1900, there was a preference for light coming from the left side. Here's an example where, like, just a random example where light's coming from the left. This was corroborated in more recent work where called Reliable Top Left Light Convention starts with early Renaissance, where they looked at 10,000 artworks and had people label where they thought the light was coming from. again, corroborated this idea that until about 1900, there was this preference. And perhaps because of if more artists, a majority of artists are right-handed, and they place a light in the scene, they might place it so that they'll shadow their hand doesn't shadow a piece of paper. So I don't know the true explanation, but there is this preference. And I'm actually very interested if this is reflected in like how people take photographs. You could imagine there might be a slight bias in how people compose photographs for lighting direction. And interestingly, okay, going back to two photos I already shown, Lincoln has this lighting coming from the left. In this John McCain portrait, the lighting is coming from the right. I don't know if that's like a political statement or not, but I just thought it was interesting that I did a non-scientific test of presidential portraits and found that indeed it seemed like more often the light was coming from the left than the right. Okay, and finally, some more work from MIT. There's other things that are very clearly asymmetric in the world. Like, okay, it says my internet connection is unstable. I hope you can still hear me. Okay, now it went off. If I'm breaking up at all, please let me know. So, the universe is asymmetric with respect to time as well. So because physics and entropy, the time physics does not move the same backwards as forwards. And you can also, oftentimes in videos, videos reveal strong directionness. So you can tell if an image is playing forwards or backwards, sometimes quite easily. And so they explore this for, self-supervision and other tasks in this great CVPR 2018 paper. Okay, so with all, that's just all a kind of prologue of exploring these interesting asymmetries in our world. And in so we wrote a paper on this last year in ECCV called Visual Chirality with Jiqiu Lin, who's now a PhD student at CMU, and Jin Sun and Abe Davis, former MIT grad, now professor at Cornell. I guess one way to think about it, we took that MIT work and dumbed it down one dimension and looked at asymmetries, explored asymmetries in space instead of in time. Okay, so I've been, this word chirality came up before. So there's this notion of geometric chirality, which is an object is geometrically chiral if you mirror flip it, and then you can't rigidly transform the thing into the mirror flipped thing. Okay, so the canonical example of a chiral object is a right hand, because if you flip a right hand, it becomes a left hand, and you cannot geometrically transform with a rigid transformation of a hand into a left hand. They're different objects in some sense. Okay, I think this term chirality was coined by Lord Kelvin in the context of chemistry. That'll come up in a second, but he called any geometrical figure or group of points chiral and say that it has chirality if its image in a plane mirror, ideally realized, cannot be brought to coincide with itself. So chirality, another term might be handedness or asymmetry in some sense. So actually, it's not too easy to come up with examples of like everyday chiral objects. So, right hands are chiral, corkscrews are chiral because the screw turns counterclockwise or clockwise. And if you flip it, it turns the other way. Golf clubs are chiral because like one, the sort of part you hit the ball with is on one side. Molecules are, okay, I tried to find a chiral object in my house. The best, I couldn't find a corkscrew. The best I could find was these scissors, which I think if you flipped it, the blades would kind of be going the opposite, overlaid on each other the opposite way. Okay, scissors are chiral. Molecules are chiral, as I pointed out in the beginning. So in fact, that's maybe the most, the way that affects the universe, the kind of chirality that affects the universe the most. And in fact, like the famous example of this from chemistry is that your nose can tell the difference between left and right-handed versions of molecules. So like the molecule that makes spearmint smell like spearmint, which is a certain variety of carbone, the right-handed variety. If you flip it, it's the thing that makes caraway smell like caraway, which is more spicy scent, I suppose. And I found this great website called Chirality and Odor Perception, which looks like it's from the 1990s, that goes into extreme detail on all of the different chemicals and all the different smells they have if you flip them in different ways. So an example is like, oh, I don't know, R-benzyl isobutyl carbonyl has a green rose fragrant note, and S-benzyl isobutyl carbonyl has a particularly interesting floral green mimosa powdery fragrance note with a very natural effect. And this might seem very silly, except I think people who study fragrances, like for perfume industry, really care about all of these things. Okay. So we have chirality. Okay, chirality is a property of geometric objects. But to formalize the kinds of things I've been talking about in images, we came up with this idea of visual chirality. So visual chirality is about distributions of images. So if you imagine all the space of all natural images, and you can assign a probability to any image, visual chirality has to do with the symmetry of that distribution with respect to left-right flips. Okay, so oops, let me go back. So you could imagine that even though left and right hands are geometrically chiral, maybe they're equally likely to appear in images, because there's like 50% of hands are right hands and 50% of hands in the world are left hands. So in terms of image distribution, the probability of seeing a right hand and a left-handed image might be equal. So that's shown here as like these 2 points have equal probability. Okay, but maybe a thumbs up right hand does not have the same probability as a thumbs up left hand, because maybe you're more likely to see a thumbs up, a right-handed thumbs up than a left-handed thumbs up, because more people are right-handed. So maybe this would be reflected in an asymmetry in this distribution, where maybe maybe right-handed left thumbs up are more probable than left-handed thumbs up, right? And so we call, in our parlance, we call such a distribution visually chiral, because the probability of these flipped instances is not equal. So to make that formal, okay, suppose we can assign a probability P of X to any image X. The probability distribution P we call visually chiral if P of X is not equal to P of T of X, where T is a horizontal mirroring operation for any X. So it's visually chiral if it's not symmetric, if the probability distribution is not symmetric with respect to left-right flipping. And this somehow captures this notion of like, is data augmentation with left-right flipping a valid operation? Does it put images in the same visual universe? If the universe is visually achiral, then it's okay. If it's visually chiral and you have this asymmetry, then at least something subtle goes wrong if you do that. Okay, so another way of saying this is, okay, Abe Lincoln's face is asymmetric, clearly. But are you just as likely to meet mirror Lincoln in the world as real Lincoln, or do faces tend to be asymmetric in similar ways, so that real Lincoln is more probable than mirror Lincoln? That's sort of another intuitive definition of this. Okay, so it's very easy to like test this with deep learning. You take a bunch of images, you flip half of them, and you train a classifier on the binary flipped, not flipped task. Okay, and if you do that, so we created a data set of people, because a lot of the ways in which the world is chiral have to do with like handedness, I think, right-handed being more prominent, more likely than left-handedness. So we created a data set of people, and then we found surprising accuracy. So our trained classifier could solve this problem with 92% accuracy. So we want to say, okay, why is it doing this? We used GradCam, network visualization method, which visualizes salient regions. And we found that, okay, it's firing on like weird like things like edges and corners. It doesn't seem to have any meaning to them. So, okay, we tried random cropping. Maybe that would break up some kind of weird artifact that's happening. Okay, now it dropped to 80%. That's probably pretty high though. So why? Okay, then we said, okay, a lot of it is due to text. If you explore the kind of salient features, they have to do with text. Okay, so we removed images of text because we want to explore more subtle chiralities. Okay, so you end up with about 74% test set performance, so still fairly high. So about 2/3 of the time the algorithm can tell, the network can tell. And this generalizes somewhat to random images as well. So random images that don't necessarily have people in them. So we took images from the Flick 100M data set and got about 55% accuracy, so better than chance. So still there seems to be some signal. And if you include images with text, that goes up to 59%. Okay, so we wanted to see what kinds of things it was discovering. So we clustered these salient regions by running GradCam, which again, like identifies things that seem to have a high influence on the classification score. So you can think of this as, this GradCam gives you a heat map. You can choose the most salient spatial location, take the feature vectors at those locations and cluster them. And we just did k-means clustering. And so here's some clusters that pop out. Okay, so shirt collar. So it's very good at telling the kind of subtle, handedness of shirt collars. And maybe, actually men and women's buttons tend to be opposite. So maybe it realizes that correlation. Shirt pockets again tend to be on the same side. So if you see a logo on a shirt, that's a giveaway as to whether an image is flipped or not. Watches, okay, more people tend to wear a watch on their left hand, on their left wrist. Guitars, people hold guitars in specific ways, especially guitars are generally made for right-handed people. You can get a left-handed guitar, I guess, like Jimi Hendrix, but guitars often appear a certain way. And then camera phones. Okay, so mirror selfies are an interesting example. Again, I think kind of deliciously interesting example where these images are flipped, but it's because they're taken in the mirror, and therefore you see a lot of people holding a cell phone with their left hand and seeing observing a flipped cell phone in the image. And that's another kind of chiral cluster that pops out. And then there were a bunch of clusters that seem to have to do with faces. And we want to explore that more. So, sort of back to the Blinken, is there any kind of asymmetry evident in faces? So we trained on F of HQ, data set of faces. And we chose F of HQ for one, because it's not a data set of celebrities where it could memorize which side of the face is Obama's mole on. It has to learn asymmetry of people in general, not asymmetry of specific people, which everyone's face is asymmetric to some degree. Okay, so it achieves about 80% test accuracy, which seemed surprisingly high to me. And then if you can also try that on just apply it directly to a different data set like labeled faces in the wild, and it gets still above chance accuracy, 60%. And so if you look at the chiral clusters of like, why is it doing this? It does seem like there is an asymmetry in hair part. Like, I think this might have to do with handedness, of the natural way you might comb your hair if you comb your hair with a comb in a certain hand. I don't think this has anything to do with human perception or preferred part direction, but just probably more physiological reasons. There's also some kind of, there does seem to be some kind of signal in beards. So there's like a beard chiral cluster. Again, this might have to do with, if you were to comb your beard, maybe you comb it with a certain hand primarily, again, if you're right-handed. Or it might also have to do with, this may also have something to do with hair part, but this is a picture of my son Charlie when he was younger, and you notice this very distinct hair whorls, and most people have clockwise hair whorls, which I suppose might affect the way their hair appears, or even maybe their beard, if somehow there's an effect on facial hair in photographs. Okay. There also seems to be an asymmetry in eye or gaze direction, to where there's, it seems to pick up on which way, very subtle differences in where people are gazing. And I don't know why. Again, this is just maybe an intriguing finding. I don't know what it says. It's worth further study. It could be that people who have strabismus, for instance, like Lincoln, it's predominantly on one side. So I've become obsessed with looking at portraits and seeing if the eyes don't quite seem to be looking exactly at the camera. So, JFK Jr., here's a People magazine cover I saw where it seems like one eye is not quite looking at the camera in the same way the other eye. Here's Denzel Washington. I don't know, this kind of effect where the eyes don't seem to be looking exactly in the same direction is something I've noticed in portraits recently. But there could be a lot of reasons for this. It could be an asymmetric placement of the lens with respect to the camera body. So when someone looks at a camera when you're taking a portrait of them, I actually don't know where they tend to look. Actually, well, maybe this gaze eye tracking that Antonio was talking about might provide some clues. There could be some asymmetry in how people tend to pose their head when they take a portrait. I don't know, maybe based on handedness or other things. It could be that ocular dominance plays a role. Okay, so everyone has a handedness. Well, I guess it could be ambidextric, but in addition to handedness, people tend to have an a dominant eye, which I don't know. There's different ways of testing your eye dominance. It tends to be, I think, if you're going to fire a bow and arrow, the eye you keep open when you fire a bow and arrow. And about 70% of people are right eye dominant. So there's also a asymmetry in eye dominance. And perhaps that has something to do with how people, if you're looking at a camera with two eyes, maybe somehow your gaze direction is affected by eye dominance. Again, these are all just random guesses. If you have some knowledge of psychology or an ophthalmologist, I'd love to talk to you. Okay, and then finally, again, going back to these low-level cues, we're very intrigued by the fact that without random cropping, it seems to pick up on artifacts on boundaries and edges. And so, compared to random cropping, where it seems to pick up on more, object type regions. So here's a question for you, which we've thought about for a while. Are cameras chiral? Are cameras chiral in a way that might have an effect on images and how left-right images appear, or real images versus flipped images? And I'll feel free to weigh in on Zoom chat if you have any theories, and then I'll reveal what we think is the answer. It's not obvious, right? It's like, well, okay. Location of the flash, yeah. That might be, I think, in a cell phone camera, that's a potential cue camera. But that might, if you hold the lamp in portrait, then the flash would be on one side. The right, okay, so it might have, yeah, the logo is certainly, the person is usually holding the camera in the right hand, including parts selecting the object. Yeah, I think there are a bunch of kind of more physiological explanations, like which eye you're looking through the viewfinder and what hand the photographer is holding the camera with. But I think there's also a physical chirality, which is, and actually Bill Freeman pointed this out to me a few years ago when I was talking about this, which is the sensor. In many digital cameras, the sensor has a Bayer filter overlaid with it. And I know I'm running out of time, so I'll wrap up very soon. Where if I take an even sized crop of the Bayer filter, then it's chiral, because on the left hand, upper left, there's a green pixel filter, and on the upper right, there's a red pixel. And so Bayer filter mosaics are chiral. If I flip them, they're not equal, but they're almost equal. Like if I shift it by 1 pixel, they will line up again. So, I think Bayer filters alone might explain some subtle effects on the boundary, but what we really observed is that if you combine that with JPEG compression, so if a JPEG is like, divides the image into 8x8 or 16x16 blocks, compresses each one separately, and because a block is like a small achiral region if you overlay on a Bayer filter, I think what happens on the kind of left side you might get a subtly different distributions of colors on the right side of the block than the left side of the block. And indeed, we did some analysis of this, and this seems the case. So the upshot is every JPEG image in the universe captured with a Bayer filter mosaic, we believe has teensy chiral traces embedded, like very low level signal saying whether that it's a true image, such that if you flip it, those low level signals are also flipped. And so even if the distribution of natural images themselves, like right hands and left hands, were perfectly symmetric, we can use these low level signals to tell if an image has been flipped. Okay, so just to finish up, so this is mainly just curiosity driven research, but there are some applications, like I think better data augmentation. You could potentially use this flipping as a self-supervision signal to learn visual representations. Like, certainly we're discovering some objects like watches in this work. You could use it for image forensics. If there really are these low-level signals, you can tell, this is another tool in your, is this image real or not toolbox. Visual discovery, just like understanding things about the world we didn't know. And I guess a very pragmatic one is mirror detection. There's this great SIGGRAPH paper on detecting mirrors in scenes, so you don't actually reconstruct the wrong thing if you're doing a 3D reconstruction. And it's just very fun to think about this stuff. So just to wrap up, I think that deep learning is a great tool for learning subtle visual correlations in the world. Like there's a whole bunch of papers on this even before deep learning, like what makes Paris look like Paris. You know, Shiri Guinness's work on how portraits evolves over time, like people smile more. You know, the work of Timnit Gebru on, you know, demographic estimation from Street View. We've also done some work on like, do people really wear white clothes more after Labor Day? By analyzing large amounts of photos. So I really hope that deep learning will be used, you know, in proper ways. You know, it's very easy to find spurious correlations too, but as a kind of tool for visual discovery. So thank you very much. I think it's 1 over. If there's time. Thank you very much.
Thank you very much. I guess there's time for one question. Thanks a lot to Noah for a great talk.
This is so cool. Yeah. And if you have any other examples you've come across of these kinds of asymmetries, I'd love to hear about them. I obsess over this, like fall asleep at night thinking about this kind of
thing. So I was wondering, especially going back to kind of your first example of the person like holding the newspaper. And he was also holding this bag in his right hand, right? So I wonder if like how much an impact kind of carrying has. Like you know, if you're like, usually people are right-handed and then they kind of might well carry things, but also their whole body pose might be slightly asymmetric and kind of, you know, oriented to one side or another.
Yeah, it's very interesting. So yeah, bodies are clearly asymmetric. I guess somehow the inside of the body is for some reason more asymmetric than the outside of the body. But there have been studies, even again, people who know psychology know this better than me, but like if you ask someone to smile, they tend to express it more strongly on the left side. I don't think that holds for spontaneous expressions because the spontaneous expressions are different than posed expressions. So I think there is difference in how muscles are activated on the left and right side, at least in certain cases. And part of that might be due to like which hemisphere of the brain is controlling which muscle. But yeah, I also, you know, it seems clear that through just living life, you might, you know, one side of your body might be different than the other side of your body, and that might show up in very subtle ways.
So do you think that's then correlated with age? Like are babies' faces more symmetric than kind of old people's faces?
That's a good question. I don't know. There might be psychological literature on this, but I'm not sure. I mean, I know that people have studied, for instance, twins to some extent, but that's a different kind of question. But I don't know about like the age kind of aspect. It's an interesting question. I think, yes, and you know, just I guess another small example of that would be like if you do tend to express one side of your face differently than the other, you could imagine like wrinkles being different in between the two sides over time. Okay, yeah, something to think about. That's a good point. I'll have to think more about that, and I'll add that to my list of things to think about.
Yeah, thanks so much, Noah, again for the great talk and very like original talk. It was great hearing all these thoughts.